An ideal Rankine cycle operates with a closed feedwater heater. The steam generator pressure is 80 bar and the condenser pressure is 10 kilopascals. The exit of the condenser is a saturated liquid. Steam is extracted at 10 bar and 240 degrees C and leaves the feedwater heater as a saturated liquid. The extraction fraction is 10%. The mass flow rate delivered by the steam generator is 80 kilograms per second. Determine the net power produced and the thermal efficiency of the cycle. Recalculate these quantities if the extraction fraction is reduced to 0. So in this Rankine cycle problem, we need to recognize what the system looks like. So it's described as an ideal Rankine cycle with a closed feedwater heater. So we need to know the components that make up that type of Rankine cycle. So we'll review what these components look like. Starting down here, we have the pump. So condensate comes out of the condenser and is pressurized by the pump from the condenser pressure all the way up to the steam generator pressure. So you'll notice there's only one pump in this particular system, so it has to get us from the condenser pressure all the way to the steam generator pressure. After that condensate is pressurized to point 2, then it passes through the closed feedwater heater. And that's where it receives heat from this extracted steam over here. So a closed feedwater heater, there's no mixing between the feedwater going through on this side and the extracted steam going through on this side. So after being preheated, the feedwater continues up and goes into the steam generator where it comes out as superheated steam. Then it goes through the first turbine, and then a small portion is extracted for the feedwater heater. So this extracted steam goes through the feedwater heater and a bunch of heat transfers from it into the feedwater. After it comes out of the feedwater heater, it passes through a steam trap, which is essentially a throttling valve, and into the condenser. So the portion of the steam here that is not extracted continues on and goes through the second stage turbine and then eventually into the condenser. So now that we've got the diagram drawn, we want to go back to our problem statement and get all of the numbers off that problem statement and put them at the right place on this diagram. So the first thing we were told there was that our condenser is operating at 10 kilopascals. So we know the pressure from the outlet of this turbine all the way through the condenser to the inlet of the pump is 10 kilopascals. The steam generator pressure is 80 bar. So that means the pressure is 80 bar all the way from the discharge of the pump up through the steam generator to the inlet of the first turbine. The extraction point here is at 10 bar. So notice that's an intermediate pressure between 10 kilopascals and 80 bar. So all of this piping from the exit of the first stage turbine into the second stage turbine and through this side of the closed feedwater heater, that's all at 10 bar. We're also told that this extraction point is at 240 degrees C. So notice the state there is fixed. The other thing we're told is that the inlet of the pump is a saturated liquid, and also the exit of the closed feedwater heater. So where the extracted steam, which is this side, leaves the feedwater heater, it's a saturated liquid. And of course, those are going to help us to fix the state. We're told that the mass flow rate is 80 kilograms per second coming out of the steam generator. And we're told that 10% of that 80 is extracted. So 10% of the flow is extracted. So that means that the flow rate in this line is 8 kilograms per second. Therefore, the flow rate in this line and through turbine 2 is 72 kilograms per second. So notice that in this problem, because we've been given the mass flow rate coming out of the steam generator and we've been given the fraction that is extracted, we actually know the mass flow rate in all of the components from that. Now the other thing that was given in the problem statement is this was described as an ideal Rankine cycle. So remember that means that the turbines and the pump have an isentropic efficiency of 100%. And we'll revisit that during the analysis. So what have we been asked to find? Well, the net power. So notice it's a rate of work transfer that we're asked to find, so W dot, and the net, so taking into account all of the work transfers with the surroundings. We're asked to find the thermal efficiency of the cycle, and we're also asked to recalculate both of those quantities if the extraction fraction was reduced to 0. So if we turned off the feed water heater, just as if it wasn't there, what would be the change in the net power produced and the thermal efficiency of the cycle? So the assumptions, this will be steady state analysis, adiabatic turbines and pumps, so no heat transfer from those components. And like I said, the pumps and turbines are reversible because this was described as an ideal Rankine cycle. We're going to neglect kinetic and potential energy, very standard assumption for Rankine cycle questions. And finally, constant pressure will be assumed in all of the heat exchangers. So for the analysis, we want to remind ourselves that the thermal efficiency of any heat engine is the rate at which work is produced, the net rate at which work is produced, so taking into account all turbines and pumps, divided by the rate at which we have to add heat into the system. So for this particular cycle, the contributions to the net power are the 2 turbines and the pump. And the only contribution to Q added is the steam generator. So this just breaks down for this particular cycle what all of the contributions to the network and Q added are. So we're going to have to figure out what all of these energy transfer rates are, and the energy equation is going to play a prominent role there. So we bring out our most general form of the conservation of energy equation for a control volume. We're assuming steady state, so that will be 0. Depending on what component we're looking at, either the heat transfer or the work transfer will be 0. We need to keep our summations of inlets and exits because when we analyze the closed feed water heater, it has 2 inlets and 2 exits. But we'll be assuming that the kinetic and potential energies are 0 at all of the inlets and exits for all of the components. So we're going to begin by looking at the pump. And remember, there's only one pump here. So since this pump is pumping liquid, we're able to calculate the work directly from the integral of V dP. Now notice here we're calculating a power. So we have a mass flow rate on the right-hand side of this equation as well. So it's negative m dot integral from 1 to 2 of V dP. And because it's a liquid pump, this specific volume is essentially constant, so it can come outside of the integral sign, and we get minus m dot 1 V1 P2 minus P1. So to get the properties at point 1, we remind ourselves that that's at 10 kilopascals and it's a saturated liquid. So table A3 will tell us the enthalpy at 1, 191.83 kilojoules per kilogram, and the specific volume at 1, 0.00100102 meters cubed per kilogram. So with that, we have all of the numbers we need to calculate this rate of work transfer for the pump. Remember that the mass flow rate through the pump is the full 80 kilograms per second. So we have 80 kilograms per second, the specific volume at the inlet of the pump, and the pressure change across the pump. So 80 bar is 8,000 kilopascals. So this gives us a work rate for the pump of negative 646.87 kilowatts. And that's negative because it's work input to the system. The next thing we need to do before we leave the pump is use the first law for the pump in order to get the enthalpy at the exit of the pump. So notice we haven't used this equation yet because we calculated the work for the pump directly. So now that we know W dot P, we revisit this equation to get the enthalpy at the exit of the pump. And we're going to need that when we move on to the next component. So rearranging this equation, H2 equals H1 minus the work rate of the pump divided by the mass flow rate. And we have numbers for everything on the right-hand side of this equation. So we can calculate H2 from that. And that comes out to 199.92 kilojoules per kilogram. So notice H2 is just a little bit bigger than H1 because work has been done on that fluid as it passed through the pump. So now that we have H2, we're ready to move on to the next component. And the next component after the pump is the feedwater heater. Now you might ask, why are we looking at the feedwater heater? Because it's not involved in any of the work or heat transfers that we need to calculate the efficiency. However, we are going to have to look at the feedwater heater because we're going to need to analyze the feedwater heater to figure out this H3, because that's leaving the feedwater heater, and that's also the entrance to the steam generator. So that's why we need to look at the feedwater heater to figure out the properties going into the steam generator. So in terms of this equation, we know both of these mass flow rates. So if we can find these other properties, then we can use this to calculate that H3. Well, H2 we just found when we analyzed the pump, so we need to get H5 and H7. And it turns out we have enough properties to figure out those quantities. So the feedwater mass flow rate, so that's m.2, is 80 kilograms per second. And the extraction fraction is 10%, so this m.7 is 8 kilograms per second. So those are the two mass flow rates that we'll be putting in there. At 0.7, so to get this H7, that's at 10 bar, and it's a saturated liquid. So table A3 will give us H7, and that's 762.81 kilojoules per kilogram at 10 bar. 0.5 is our extraction point, and we were told the pressure there, 10 bar, and the temperature, 240 degrees C. So table A4 will tell us that H5 is 2920.4 kilojoules per kilogram. So now we have everything in this equation except H3, so we can substitute all of those numbers in and solve this equation for H3. And when we do that, we get an H3 of 415.68 kilojoules per kilogram. So this is the enthalpy of the feed water leaving the feed water heater. So that will be the entrance to the steam generator. So notice that's a fair bit bigger than the enthalpy entering the feed water heater, which was this 199.92. So later on, when we turn off the feed water heater, the effect is going to be that this will be the inlet enthalpy to the steam generator rather than this higher 415.68. So now, though, we can move on to the steam generator. So first law applied to the steam generator tells us that the rate of heat transfer into the steam generator is the mass flow rate through the steam generator times H4 minus H3. So H3 we have, that's why we looked at the closed feed water heater, was to get H3, but we need H4. So that's the inlet to the first turbine. The exit of the steam generator is the same point as the inlet to the first turbine. Now at this point, the only property we know there is the pressure. It's 80 bar. So we need another property at 0.4 in order to be able to calculate the enthalpy. Well, if we look ahead to the first turbine, we realize it's an isentropic turbine because this is an ideal Rankine cycle. So that means that S4 equals S5. So the entropy at 0.4, which is the point we're currently interested in, is the same as at 0.5 because it's an isentropic turbine. Well, 0.5, the state there is fixed because we know a pressure and temperature. We already used that pressure and temperature to get the enthalpy. So we just need to go back to the same place in table A4 with a pressure of 10 bar and a temperature of 240 degrees C and get the entropy, and that turns out to be 6.8817 kilojoules per kilogram Kelvin. So now we have two properties at 0.4 that we can use to get the enthalpy. So with a pressure of 80 bar and an entropy of 6.8817 kilojoules per kilogram Kelvin, table A4 tells us that the enthalpy at 0.4 is 3524.6 kilojoules per kilogram. So now we're ready to finish off this calculation of the heat transfer rate into the steam generator. So that is 80 kilograms per second times H4 that we just found here minus the H3 that we found from the closed feed water heater. And this gives us a heat transfer rate into the steam generator of 248.71 megawatts. Now we move on to the high pressure turbine. So the work rate, or the power produced by the high pressure turbine, will be m dot 4 times H4 minus H5. And we know both of these enthalpies as it turns out, so we're ready to substitute numbers in there. There is full flow through this first turbine, so we have 80 kilograms per second there, and the H4 and the H5 that we already know. So the power of the first turbine is 48.336 megawatts. Now we move on to the second turbine. So the power of the second turbine is the mass flow rate through the second turbine, which I've designated here as m dot 6, times H5 minus H6. So we need to figure out the enthalpy at 6. We know the enthalpy at 5 because we use that for the high pressure turbine. Well, at 0.6, the entropy is the same as at 5 because the second stage turbine is also isentropic. So that's that same value of entropy. And the pressure at the exit of this turbine is 10 kilopascals, the condenser pressure. So table A3 will tell us that at 10 kPa and an entropy of this, the enthalpy is 2,179.98 kilojoules per kilogram. So now we can calculate the power produced by that second turbine. We need to remember, though, that the flow rate through the second turbine is only 72 kilograms per second because of the extraction. So the power for the second turbine, 72 kilograms per second times H5 minus H6, and that gives us a power for the second turbine of 53.31 megawatts. So now the net power can be produced because we've got a power for both of the turbines and for the pump. So reminding ourselves that the net power is the sum of those three powers. We go and get the three numbers we just calculated and we add them all up, remembering that the pump power is negative, so we got to carry that sign in when we substitute for the W dot P, and that gives us a net power of 101 megawatts. So this is the net power output of that Rankine cycle because it's taken into account the power that is required in order to run the pump. So we conclude that the net power of this cycle is 101 megawatts. Moving on to the thermal efficiency, remind ourselves that that's the net power, which we just calculated, divided by the heat transfer rate into the steam generator. So we have both of those numbers. So 101 megawatts divided by 248.71 megawatts gives us a thermal efficiency of 0.40609. So we conclude the thermal efficiency of this cycle is 40.6%. Now the last part of this problem was to recalculate these two numbers if the closed feed water heater was turned off. In other words, if the extraction fraction was set to 0. Well, that's going to have two effects. And I'm just going to go back to the schematic diagram to discuss this before we go ahead and do the calculations. So when the flow through this line is set to 0, the first effect that we're going to see is that there's no longer going to be any heating happening here. So whatever the properties are at 2, that feed water is going to pass through the closed feed water heater with no change in properties. So the first effect that we'll be recalculating is that the heat added into the steam generator is going to have to be bigger because the inlet enthalpy for the steam generator will now be our value of H2. So essentially H2 and H3 will become equal if this extracted steam is closed off because there'll be nothing coming through here to preheat the feed water on the other side of this heat exchanger. So that's the first effect. We're going to have to add more heat into the steam generator because there's no preheating of the feed water anymore. The other effect that closing off this line is going to have is that the full 80 kilograms per second now is going to go through the second turbine. So the flow through the two turbines will now be the same. So the flow through this turbine is going to increase from 72 kilograms per second up to 80 kilograms per second. So this second turbine is actually going to produce more power. So we'll need to add more heat into the steam generator, and we'll get more power out of the second turbine. So we'll see what the net effect of that is on the efficiency when we do the calculations. So as I said, when the extraction is turned off, the feed water heater no longer preheats the feed water entering the steam generator. So we redo that calculation, and the difference now is this number is a lot lower. If you go back, you'll see that this is the value of H2. So essentially we've set H2 equal to H3. The flow rate is still the same, and the exit enthalpy is still the same, but this has reduced. So that gives us an increased heat transfer rate into the steam generator, and our new number is 265.97 megawatts. The other effect is that we have full flow 80 kilograms per second through the low pressure turbine. So we do our low pressure turbine calculation again. The two enthalpies are the same. The only thing that's changed is this used to be 72 and now it's 80. So the new power produced by the second turbine is 59.234 megawatts. So now we can calculate the change in the net work and the thermal efficiency. So the net power is the same except for this number here, because that's our updated value for the power produced by the second turbine. The first turbine and the pump still stay the same. So this gives us an increased power of 106.92. Remember, the old power was 101. So the power output, the net power output of this plant has gone up to 106.92. So we conclude that with the extraction turned off, the net power of this cycle is 107 megawatts. Finally, the new value for the thermal efficiency can be calculated. So we take our new power here, 107 megawatts, divided by the new value for the Q in the steam generator. So that also went up, 265.97 megawatts. So both the number in the numerator and the denominator both increased. However, the net effect of this is that the thermal efficiency goes down. So it's now 40.2%. Remember, it was 40.6% when the extraction was 10%. So the effect of the feed water heater is to increase the thermal efficiency of this cycle. It does reduce the power output, but it increases the thermal efficiency. So our last conclusion here is that with the extraction turned off, the thermal efficiency of this cycle is 40.2%.